Good afternoon, everyone. My name is Elfrida Hall, and I am the project manager for the Commercial SmallSat Data Acquisition program. And I would like to welcome you to the CSDA Lunch and Learn. We will be featuring Spire commercial data that we have under the program. The logistics here would be, if you have any questions, please put them in the chat, and we will be monitoring them throughout the session. We will plan to have a question and answer session at the end, if time permits. Please, just wanted to let you know also that this lunch and learn is being recorded. If you have any objection, please let us know now. But we are recording, so it will be available later. I would like to also bring to the table Will McCarty. He is the program scientist. And Will, if you want to come on and say a couple of words, that will be grateful. And after Will, we will turn it over to Spire. Jeff will basically introduce Spire along with the team members.
Okay, so yep, thanks you, Elfrida. So yeah, I'm Will McCarty, program scientist for CSDA. I've been with CSDA since, I guess, before the beginning of CSDA, from the initial pilot, where I was actually one of the evaluators for the Spire radio occultation data. So I was on that initial group, and actually ended up leading that initial group in terms of getting through the initial data pilot. And with that, I worked when I was formerly the project scientist for CSDA. Worked with Spire through that. So I've really kind of been involved through the whole process. Now I'm at headquarters. I'm a programmatic side, so working with CSDA from that level, and also always considering how these data fall into my focus area, which is the weather and atmospheric dynamics focus area. So with that, I'm very happy to be here. I'm glad I was able to make it. It was kind of question mark up until the last minute, but happy to be here, and I'll hand it over to Spire.
Thank you so much, Will. Thank you so much, Elfrida, for the warm introduction. My name is Jeff Bryan. I'm a program manager here at Spire Global, helping coordinate our efforts under the NASA Commercial SmallSat Data Acquisition program. I'm here today during this lunch and learn to introduce a few people, and we're going to step through the products that we have available under the catalog. Without further ado, I'll jump right in. So throughout this presentation, you're going to hear from some of the following people. Dr. Nguyen, our GNSS-RO Scientist, has been with Spire Global for many years. Probably a name you've seen before on some of our products. I'll also introduce Dr. Phil Jales. He's our Bistatic Radar and GNSS-R Reflectometry Specialist. He's been with Spire as well for many years, working on our reflectometry and Bistatic Radar products. And then Hunter Garbacz, an account executive here at Spire Global, managing some of our federal programs, including NASA. Without further ado, I'll turn it over to Hunter to get us started.
Thanks, Jeff. If at any point you can't hear me or what have you, let me know. Next slide, please. So thanks again for having me. I've supported various programs here at Spire, primarily focusing on our global data services within the maritime and aviation domains, but I'll provide a brief overview here of Spire's mission and architecture and its future steps on the space services end. We can jump to the next slide. So Spire utilizes its LEMUR constellation, low Earth multi-use receivers, primarily made up of a 3U form factor. We are now expanding and have expanded to a 6U, and as customer needs require, to the 12 and 16U bus sizes. And so on the ability of our constellation, utilization of our global coverage, we're able to provide multi-domain RF awareness, and we operate the world's largest RF sensing fleet. As everyone here is aware, and we'll be going into on the radio occultation, weather, and space weather awareness that we're able to provide. We also do supply various commercial and federal customers within complete and comprehensive global coverage of the maritime domain through systems such as AIS identification, automatic identification systems. And we're able to refresh and downlink our data due to a global ground station network that we operate, have deployed and operated. And we're on some products able to have real-time latency and or in other cases near real time. And that also applies to the aviation domains. The key here is one side of our business is focused on our global data services. And in addition to that, we're able to launch custom payloads and help interface custom solutions as their needs require and get their systems up in the space in a very short period of time, between 6 and 12 months. We can jump to the next slide. So this is providing a map of our current ground station antenna system network. This, just simply put, allows us to provide that low level of latency and global coverage by not having to rely on third-party ground network, and overall is a backbone of Spire's services on the data side, as well as we expand our space services business. We can jump to the next. So across all of our product verticals, as I previously mentioned, we do a lot here at Spire, and it's an amazing opportunity to work for this company and have so many different conversations across the board. And so, as I mentioned, if we want to focus on the right-hand side here within the maritime, aviation, and weather domains, we do provide comprehensive awareness, active analytics within each one of those domains. For maritime and aviation, many federal end users that utilize our data sets and our real-time awareness for either maybe research or operation-oriented programs. And then weather, again, which we'll be talking thoroughly about today, but active collection of RO and the largest commercial provider of RO data, and provide a lot of weather variables that can have utilization across many different types of use cases. In addition to that, we're always expanding, and I'll let Phil and Vu and dive into our Earth intelligence and GNSS-R and overall awareness and support as Spire develops these capabilities and shares that data with the likes of everyone here today. We can jump to the next slide. So the backbone of Spire's LEO constellation is that 3U carrier. As customer needs require and overall the payload dimensions increase over time for some of the use cases that we support, we are expanding to a 6U within our LEO constellation. And there's a lot of different benefits between the 3U, 6U designs, everything unique to our vertical integration here at Spire. We're able to support a wide array of payloads for our customers. And it's a very unique position to be able to refine our space services and overall our 3U and 6U, and as the next slide will indicate, 12 and 16U carriers to customer-oriented needs. And feel free to review our website as well as get in touch with us directly if you have specific questions regarding any of our spacecraft. And we can jump to the next slide here. So as the industry in some cases looks for a larger carrier, in this case we are working with Northstar to develop and deploy in Q3, Q4 of this year, or this next year, I should say, 6 16U satellites, as well as additional commercial customers utilizing the 16U carrier. And then in addition to that, we will be focusing partially due to Northstar on launching additional carriers in Q3 of next year. And again, this just pushes up that overall payload power and voltage to customer requirements. and is definitely a step forward that we'll see here across the space services mission here at Spire. And we can jump to the next. So thank you. I think handing off to Vu here on our CSDA program data products.
Okay, thanks, Hunter. Yeah, this table here shows an outline of the NASA data products that we provide through the CSDA program. I'm not going to go into too much detail here because we should probably provide a little bit more detail on each of these products throughout the presentation first. But you can see that most of our products are available starting at around 2019 and covers through the present period. These data are available at a 30-day delay, and these products, before they're introduced into operational use, they undergo a NASA evaluation, and we continue to make improvements available as they are developed. So we should just probably jump into the radio occultation details now. Next slide. All right, I'll first be covering GNSS-RO, or radio occultation. Next slide. Before I begin, this schematic here shows an overview of our Spire Earth intelligence data. So you can see that each of our satellites is equipped with a GNSS receiver on board and orbiting in low Earth orbit. In the radio occultation case, as shown in the red line, the GNSS signal transmitted by the satellite traverses through the Earth's atmosphere and then is collected by our receiver in low Earth orbit. And then by measuring the amount of bending that the signal encounters along its path, we can then derive profiles of atmospheric bending angle, refractivity, and temperature, which are important for numerical weather prediction primarily. In recent periods, we've also added the capability of collecting GNSS reflected signals as well, or GNSS reflectometry. These data carry information about the Earth's surface, including soil moisture, ocean wind speeds, and sea ice properties. That will be covered later in the presentation by Phil Jales. Next slide. The picture on the lower left here shows an example of what our GNSS-RO satellites look like in space right now. So you can see on the top portion of the satellite, there's a single patch antenna that we call this the POD antenna because it's primarily used for precise orbit determination purposes. This antenna is designed to track as many GNSS signals as possible. These signals are also collected at dual frequency. So as a result, they can be used to derive ionospheric TC measurements as well, which I'll cover a little bit later. On the fore and aft sides of the spacecraft, you can see there are three patch antennas. These are the RO antennas that are used to collect the RO signals that are being refracted by the Earth's atmosphere. Because we have two antennas, we can track both rising and setting events at the same time. And we track multi-GNSS constellations through these antennas, including GPS, GLONASS, and Galileo. The schematic on the right shows our current configuration settings for RO collection, divided by the RO antenna on the left, and then the upwards-looking POD antenna on top. If we start at the bottom, you can see that the collection of RO events for the neutral atmosphere start at around 170 kilometers line of sight altitude, and then extends to below 200 kilometers below the surface of the Earth. The neutral atmospheric tracking is done in open loop tracking mode in order to track the signal down to the lowest part of the troposphere. And this is done at a high rate sampling of 50 hertz. In addition to the neutral RO tracking, we also perform closed loop tracking to produce phase and pseudo range measurements at 1 hertz, and those will be used for space weather and POD estimates, which I'll cover later. Right now, we have over 40 RO capable satellites in low Earth orbit right now, and we currently task over 25 in RO production. Next slide. So once we collect the data and download them using our ground station network, we process these data into all data levels using our processing system. We primarily use the UCAR's CDAC conventions for these products. So these include the level 0 low-level phase data for each RO event, and these are contained in a netCDF format for easy use. We also provide the atmospheric excess phase delay estimates contained in the atom phase netCDF format. And then finally, we also provide the atmospheric bending angle refractivity in a netCDF format or atom prof, as well as buffer for numerical weather prediction assimilation. For each RO event, we also provide the POD estimates and underlying GNSS data observables. So these are contained in a RINEX format as level 1A POD OBS products, attitude data, and then as well as the precise orbit termination estimates that we provide in LEO orb. The plot on the right shows an example comparing our bending angle estimates compared to ECMWF analysis in terms of the mean difference and the standard deviation of the difference on the right. And for the most part, our comparison is comparable to other missions, and these are divided by different constellations here. Next slide. Here's the current status of our RO production right now. So you can see on the plot on the lower right, we've increased our RO production from just over 5,000 quality control profiles per day to about 20,000 quality control profiles per day. This threshold is important because this is currently the amount of data that IRWG and the CGMS targets in terms of quantity. So we're particularly happy to meeting that threshold recently. And we also have the ability to scale up this number pretty quickly given the future demand. The plot on the lower, on the right shows our current coverage as well. You can see on the latitude local time plot in the lower right, you can see that we cover the majority of local times quite well. We still have some gaps in around the 18 o'clock local time plane, and we're hoping to fill that gap in with future launches. So these data are available, most of these data are available to NASA with a 30-day delay. We also are delivering raw and processed data to near real-time major processing centers such as NOAA and UMETSAT, which then process our data and then further disseminate that data to NWP centers for assimilation and use. Next slide. Over the past couple years, we've had many third-party evaluations from UMETSAT, UCAR, and NOAA, which have evaluated our RO data at the observational level and as well as the NWP impact level as well. So the study, the plot on the right here highlights a study conducted by ECMWF in midway through 2020 at the start of the pandemic. During this time, Spire delivered our RO data for several months for ECMWF to assimilate into their model. And you can see by the orange line in around May 2020, the introduction of Spire data resulted in an increase in their FSOI score during this time. The study on the left, or the plot on the left, highlights a study conducted by UCAR where they extracted planetary boundary layer height processed where they processed Spire data. And they were able to produce this map and noted that Spire's penetration depth exceeded many heritage missions, which made this measurement possible. Next slide. A couple more studies that were highlighted at recent IRWG, or International RO Working Group meetings. ECMWF continues to assimilate Spire data in near real time and has shown that the impact of Spire data is comparable to other missions such as Cosmic 2. NOAA has also performed an analysis of Spire's penetration depths and compared it to other missions, and then shown the penetration depths to be quite similar. And then finally, the study on the bottom here was conducted by Will McCarty in the audience, where he used Spire data in the GEOS model and showed that Spire RO data could have a positive impact during this time period. Next slide. Okay, now I'll briefly cover the space weather data. So as a refresher, I have the same schematic that I showed earlier, showing our current configuration settings for each of these antennas. If we now focus on the closed loop tracking part of the schematic, those are primarily the measurements that are used to derive ionospheric TEC measurements, because these signals are collected at dual frequency. You can see for the RO antenna, the tracking of ionospheric RO events starts at around elevation 0 degrees with respect to the orbit local horizontal, and then extends downward to about 70 kilometers line of sight altitude. So basically covering the F and E region of the ionosphere. We also track these signals through our zenith-looking POD antenna as well. And then we keep an observational overlap between the GNSS signals collected through the POD antenna and RO antenna in order to provide a more continuous tracking of a GNSS satellite as it descends from a maximum zenith viewing angle down to 70 kilometers line of sight altitude. In terms of data products, what we make available, we make available the raw GNSS observables contained in RINEX format. We produce total electron content estimates from these GNSS phase and pseudo-range observables, and we make these available through our PodTech and IonTech NetCDF format files. Our receiver also produces onboard scintillation indices. And then finally, we also produce some electron density profiles as well. Next slide. So as I mentioned before, we routinely derive ionospheric total electron content, or TEC, from our GNSS observables. We do this by taking a linear combination of the phase and pseudo-range observations. We then perform a weighted leveling scheme to it, while performing cycle slip correction, and then also estimating the transmitter and receiver differential code biases, or applying them to produce absolute tech measurements. And for a single antenna, these TEC estimates are contained as observational arcs and then stored in the UCAR PodTech format. More recently, we've also produced an upgraded product of called IonTech, where we combine observational arcs from single antennas or from multiple antennas to produce a longer observational arc. And as a result of this, we produce over 5,000 ionospheric tracks per day, spanning from a maximum elevation angle to less than 90 kilometers altitude. Looking towards the future, right now in closed loop tracking, we only track the GPS constellation. In closed loop mode, we plan to add other constellations in the near future to increase the number of ionospheric tracks. Next slide. Also like to highlight our high rate data that are primarily used for the RO, neutral RO events. But because they extend to 170 kilometers or 150 kilometers and downward, they can also be used for E-region ionospheric studies. The advantage of these data are that they're high rate, and as well, they're obtained from non-GPS constellations as well. Our receiver also produces an onboard estimate of the S4 scintillation index as well. This S4 index is used to trigger on high scintillation events, and when that occurs, we actually download the entire 50 hertz high rate data from orbit altitude downwards for research use. Next slide. Okay, next slide. And then finally, just one brief mention on the precise orbit determination data. These data have been used by researchers in the community to produce neutral density estimates from our POD estimates. And then there are other applications that these data can be used for, including detecting mass change, trend signals, which have yet to be uncovered, but could have some potential use here. So I'll now pass it over to Phil Jales, who will be covering our GNSS reflectometry measurements and products.
Thanks very much, Vu. So I'm going to go through our two different categories of GNSS reflectometry. So we're going from, we've gone through from ionosphere, charged atmosphere, into the neutral atmosphere and now we're going down to the surface of the Earth. So if we go to the next slide, please. So our two categories here are based on either side of the booster angle of reflections, either at grazing angle or near nadir, and we call the near nadir conventional GNSS-R. And either side of this, the grazing angle GNSS-R observations are reusing our radio occultation satellites, and so these are operationally being used on up to and sometimes over 25 satellites. And the conventional GNSS-R is what we're building up to. We've currently got 4 satellites on orbit, and these, instead of looking at grazing angles, these look near nadir. And so the difference between the two types of satellites is all about the antennas. And so in grazing angle, the signals predominantly are right-hand circularly polarized, and when we're looking towards near nadir, they're predominantly left-hand circularly polarized. And so we have these two different antenna concepts, but both of these GNSS-R payloads are based off of the same processing backend and same receiver, and therefore they contain in common some of the same key features, like multi-GNSS processing, so that we can get the most observations out of each of our satellites. Where they start to differ, though, is our processing. The grazing angle reflections, we are targeting coherent reflections, and so we perform complex signal processing and output at 50 Hz in much the same way as for radio occultation, but instead observing the Earth's surface. And so this is primarily applications focus of ice characterization, and using that complex 50 Hz output for carrier phase altimetry. The conventional GNSS-R near nadir is using a processing approach tuned to incoherent reflections, like the UK TechDemoSat and NASA Cygnus missions. And so this is forming delay Doppler maps. And the primary application we're targeting here is for producing long-term high-resolution soil moisture observations. So if you could go to the next slide. So we're going to focus firstly on the grazing angle. So again, next, please. So the grazing angle is reusing our radio occultation satellites. So up to and sometimes over 25 satellites being used in this in various orbital planes, and it's a stable operational data collection. And so we collect more than 2,000 events every day that we run through our processing system, and these range from several seconds to nearly 6-minute long tracks along the surface of the Earth. We're outputting at a high rate of 50 Hz, and we're outputting the phase information, which is the first time this is really being done operationally in this scale. So we perform open loop tracking of the direct and reflected signals, and the purpose of doing the same measurement in both direct and reflected so that they are, can be compared, and by performing the same processing for each, it makes it possible to get some of the receiver effects removed. And other aspects that are non-surface related is the ionosphere. And so, being based on the radio occultation payload, the antenna system is dual frequency, and L1 and L2 using GPS, E1, E5 for Galileo. And so, so we perform the ionospheric corrections as well. And as this is an operational constellation, it has a median latency of 90 minutes from data collection to the level 2 product availability. And so we make available through CSDA the level 1 data products of the raw observations, and then level 2, which we perform retrieval to get ice extent and ice classification and then also altimetric height profile extraction. So if we go to the next slide, I'm going to talk about how this grazing angle technique, it's calculating, it's an altimetric sensor effectively, but it's the carrier phase delay, and it's using coherent reflections in the elevation angles of 5 to 30 degrees. And these grazing angle reflections maintain coherency for up to small roughness levels of the surface. And this is one of the reasons why we can do this on the grazing angle geometry. So the precision that we can approach here is similar to that of conventional altimeters by using the carrier phase. And so we see on some tracks less than 10 centimeters root mean square error, comparing our observations to a model C surface. And the median is 16 centimeters. So that 16 centimeters contains partly the observation of how much the surface is varying. So these measurements can potentially complement other altimeters and fill in the gaps. It's operating on up to 25 satellites, and that means that we're presenting an unrivaled data quantity compared to traditional altimeters. So if you could go on to the next slide. So this paper, I'd encourage people to look at if they want further details on how these observations are formed. And the data products that we generate include this low-level 50 Hertz open loop tracked IQ data for the direction reflected, and this is in NetCDF format. And then the next stage is that we provide georeferencing and extract observables out of that data, including the altimetry, but also including reflectivity and other surface characteristics to do with the roughness. This is level 1B in NetCDF format. And then we then use these level 1 products, and we have level 2 ice extent and classification for sea ice, and then a height profile extraction as well. So if you go on to the next slide, I can show you some results here from our, of measurement coverage. And so the number of observations we're taking over 1 week is really providing something that's an observation that is kind of unprecedented in terms of an altimetric sensor, because we are tracking up to around 6 reflections at the same time. And then this coverage can then be extended and scaled up. At the moment, we focus our priority on radio occultation, but if we focused more on the radio occultation measurements and gave them more priority, we could be scaling up the number of observations by another factor of 4 on a per satellite basis if we applied that priority. So if we go to the next slide, there are a huge number of observations that we're generating this way, but what are we actually seeing? So the level 1 and level 2 SNR is correlated, and we're seeing the transitions between sea ice and open oceans. And in this case, we're seeing this at 80 seconds. So we can see here characteristic detection between ice and water. And when we are looking along the along track, we can see residual height errors. On the bottom left plot is comparing the Spire retrieval to modeled sea surface height, and then the bottom right hand plot is showing the difference between the model and the Spire retrieval. And so we are seeing sea ice effects and in our data. And so it's important to note that this is carrier phase altimetry, and therefore there is the measurement is a relative height along the track rather than an absolute measurement. So one of the ways in which we validate this, our measurements, is through bulk comparisons and bulk statistics, but also we look at co-locations. The next slide is looking at one of the ways of co-locating. So if we go to the next, so this slide is showing co-locations between two of our satellites at the same time, and we're seeing a good self-consistency in the profiles, which, because we've got multiple satellites, it is providing an intrinsic method to validate the data that we're collecting. And we've also been extending this to co-locations with Sentinel-3 altimeters. I'm going to go, in the interest of time, on to the next, which is that it's not just the altimetry that we are extracting from these observations. The other observables that are related to the surface roughness and dielectric constant properties of the surface. So here we've got one of our observables, the phase noise, and these are being plotted out on monthly maps through some of our data collection history, and we can see temporal and spatial variations in patterns of the roughness, and you can also see quite clearly first year and multi-year ice. So we've been generating a retrieval product which is available through CSDA, and that's on the next slide. The first part of this is the ice extent. So we have a simple classification algorithm to give ice extent information, and then if we go straight to the next slide, then we are then classifying in between first year ice and multi-year ice as well. And so both the ice extent and the classification are giving very good agreements to other sensors and also analysis products. We're actually in the middle of performing an update to this to turn this in from a two classification product, first year multi-year ice, into a three classification product to give further information about the ice surface. So we'll now go on to the next section. So this is what we call conventional or near nadir GNSS reflectometry. And so if we go to the next slide, I'll just give back this overview. So in this case, we're now using these antennas that are pointing down towards nadir. And these are characterized by elevation angles of 90 degrees down to 20 degrees. And we perform delayed Doppler map processing in a similar way to the NASA Cygnus mission. And if we go to the next slide, we can see that the products that we generate on the 4 satellites that we operate for this, we launched them in 2 batches, batch 1 and batch 2. And the products that we output are level 1B land surface reflectivity, which is this along track surface reflectivity product, and level 1B ocean normalized bistatic radar cross section. So these are our level 1 products which are tuned for land and coherent reflections. That's land and ice, and then the non-coherent reflections predominantly over the ocean. And then we have two retrieval products that we output from this: level 2 ocean wind, wind speed, and ocean mean square slope. And we also output a over the land a soil moisture product as well. And this one is currently under NASA evaluation prior to being included into the CSDA archives. So one of the if you go to the next slide, one of the things that Spire has got as this rich set of data, because we can link together the grazing angle data and the near nadir data. We get a really rich set of observables, because with these different payloads, we're getting dual polarization and dual frequency. We're getting coherent observations and incoherent observations, and a diversity of geometry too. And the GNSS reflectometry provides us a resolution that's between the synthetic aperture radar products and the radiometer ice products, provides a complementary view of the surface. And you can see that by combining these sets of observables from the different satellites, they're picking up different aspects of the ice surface. We pick out a box zoomed in region here, and we can see that we're picking up different aspects of the ice in each case. The next product on the next slide is our ocean product. So these are from the near nadir GNSS-R satellites, and in this case we make some comparisons between Spire wind retrieval and the Cygnus wind retrieval. So the left-hand plot is comparing the wind observations. The center plot is comparing the mean square slope, and the right-hand plot is comparing the normalized bistatic radar cross-section. So I'll summarize this as saying that we see very similar statistical performance to Cygnus in terms of our ocean wind speed retrieval. With our existing satellites, we've been focusing on the land observations, and for that we widen the antenna beam to be able to pick up a lot more reflections. But that means that we don't quite see the sensitivity needed for the high ocean wind speeds. So Spire has a cutoff where we don't produce wind speeds above 12 meters per second in output. The next slide, I will thank the University of Michigan for producing under evaluation of Spire's level 2 ocean wind speed product. And this is another way of looking at how the Spire level 2 ocean retrieval compares to Cygnus. So there are a number of different Cygnus products compared here, and the y-axis is the wind speed difference or bias in the observable. So we're looking for something to be close to 0 in bias. And the Spire observations from one of the Spire GNSS-R satellites, FM109, is the black curve around the end of here. And so we're close to 0 bias, and which is showing good performance. And we've got this is showing bias, but there's also equivalent for root mean squared error. And we show similar performance to Cygnus, but as I say, we're not picking up the high wind speeds with our current satellites. So this brings us to more where Spire is actually putting more focus in at the moment onto the soil moisture. And this is what we've been choosing our satellites for. So the GNSS-R, we've been tuning our satellites towards soil moisture. And for this, the purpose is that compared to other active and passive remote sensing methods that are used to measure soil moisture, GNSS-R has the advantage of increased moisture sensitivity and better penetration of foliage. That's due to the L-band signals providing greater penetration than say ASCAT into the soil, and also the forward scattering. It particularly picks up the inundation. So we've generated a level 2A surface soil moisture product, and it's a change detection algorithm that calibrates the surface soil moisture. It retains the along track structure of the GNSS-R sampling characteristics, and you can see on the bottom left hand plot here how we went from the our batch 1 coverage, which was in the Cygnus-like mid-inclination orbit, and then we added batch 2 that gave us full global coverage. And you can see the changes in reflectivity that are due to soil moisture changes and also due to freeze thaw. And on the right hand side we see some images which are false color showing seasonal changes in reflectivity and how these reflectivity changes with the seasons. So the next slide shows some track-wise comparisons between Spire and SMAP soil moisture. And so the soil moisture shows comparable quality to SMAP, but it has an inherently smaller footprint. And I'm not going to dwell on this slide, but go straight to the next one, because we've been doing a number of regional and spatial comparisons between Spire and SMAP soil moisture. So on the top left here, you can see the Spire GNSS-R data smoothed out or averaged even to a 24-kilometer grid. And it has got the same spatial characteristics as SMAP on the bottom row. And then if we compare our soil moisture data to SMAP on a point-by-point basis over regions, that's what we see on the right-hand sets of plots, where we're showing that we're producing soil moisture that's quite comparable to the SMAP soil moisture. So I'm going to pass on the baton now, but at the moment we've got. I'm just going to finish by saying at the moment we're delivering data with these 4 satellites from the conventional or near nadir GNSS-R, but that Spire has got this history of being able to scale up the observation quantities rapidly, and so we're partly looking at trying to understand what the demand is for the data before we scale up the GNSS-R constellation. So we'd be particularly excited to hear from people on this call if you want to give us further information about how you think these measurements could make an impact. Okay, so I'll hand on now.
Thanks, Phil. We can jump to the next slide here. So yeah, as previously reviewed by Vu, these are the available Spire products currently available under the NASA CSDA program. And we're actively, as we work with everyone who has access, which you'll see on the next slide here, to the CSDA data, we're always trying to see how we can improve our products available and make those refined in a way that can support everyone's different projects and mission scopes. And next slide. Next slide, please. Thank you. So in regards to the end user license agreement, we come across many individuals within the US government that are unaware that they have access to the CSDA program. So I spend ample time providing information about the CSDA program and connecting the various contacts to individuals that spoke here today. And it's primarily important for us, as well as NASA yourself, to expand this program and provide our data as well as additional data types to everyone that could have access. So this just indicates who does have access. If there's any questions in regards to that, you can follow up with us directly and we can work through your exact program and determine which data types you need. Next slide. And I think handing it over here to Vu.
I can take this one, Hunter. Thank you very much. So, accessing the data, the question that we've been circling around, all of these different data types that are available through the catalog. We want to make sure that folks who have projects, who have use cases, who have missions that could leverage this data have access to it. So the information is here on the NASA CSDA program website, which is available through the SmallSat Data Explorer listed here on the links on the screen. I believe this information will be provided to you separately in a PowerPoint or a PDF after the presentation. The steps listed on the screen require users looking to get access to this data to get an Earth data login, at which point you can navigate to the SDX website and search for the data sets that you want, geofenced by area or by time, and then request that data, at which point a reviewer will evaluate that claim and then provision you a link to that data set. You'll be able to download it. Acknowledging that we're close to time, I'll jump into user support. As Hunter just mentioned, there's different ways to reach out to both Spire and NASA for support in accessing the data, or if you have questions and want to speak to the experts or folks who are very familiar with this data. So if you are looking for access support, there's a contact us link at the bottom of the SDX page that'll send you to NASA, where you can speak with the experts over there on exactly how to extract this data from the system. Separately, if you have requests about use of the data or want to chat about upcoming products and how we've been evaluating the data ourselves, you can navigate to the Spire website and fill out the requested information on a sheet. And one of our sales engineers or account executives like Hunter will reach back out and solicit some information from you, and we'll have a conversation about access, about use cases, and follow up. With that, that concludes the formal presentation. I'd like to thank Vu and Phil and Hunter for their presentations today, as well as NASA for hosting this. Contact information for everybody presented is listed here on this slide. With that, I'll turn it over to Alfreda. We can start a Q&A. I think there were a few comments in the chat that I can't see at the moment. So maybe she can help with reading those out.
Okay, what I'll do look like in terms of the comments that came on, they were pretty much Spire related. So maybe Jeff, if you could come off of your video, you may be able to see the questions in the chat. Let's see.
I see it. Yep.
Okay.
Alfreda, if you would like me to as well, the folks that provided the questions in the chat, I can make them unmute themselves if they wanted to add more context.
Okay, that would work. That would work too, Kristen. So, Jeff, you can go through the comments there, and we can have the individuals unmute if they wanted to add anything. But I believe my brief selection through there looked like they're all related to you guys. So if you can answer those questions, that'll be great.
Perfect. I see Stephen has already. If you'd like, Stephen, I can read your question aloud, and if you'd like to add any additional context. The question is, what was the motivation for upgrading from a 3U bus to a 6U bus? And I will pass that over to Hunter.
Thanks, Jeff. Yeah, the motivation is primarily oriented towards customer requirements, customer payload metrics, and in addition to that, within the Spire constellation, providing for potentially a greater level of swap for our own internal payloads. And so and then in addition to that, as we expand to 12 and 16U, those are primarily customer oriented, as they require multiple aspects that are just only supported by a bus of that size.
If it's okay, I can ask a quick follow-up. does that mean that you want to have allow combined services that you usually offer through Spire, but have basic capabilities all on the same satellite rather than just have to apportion, one service out to one satellite and another out to another satellite type?
Yeah, so in regards to the available payload availability within a Spire satellite, we can support customer payloads within a Spire-driven 6U design, if that answers your question, and combining the two. But as we expand to larger buses, that's primarily oriented towards the majority of all the payload will be supported or used by that customer.
And I'll also say, to add to that, as we scale up the form factor of our satellites, it enables us to do more activities on orbit. So for example, our RO satellites can also collect and have payloads for capturing maritime signals. So the idea is, with larger and larger form factors, you can really pack in more capability on a single
Okay. I do have one other question, but I think I should let some of these other fellows ask.
Yeah, Stephen, let us, you can reach out through that customer support, and anybody on the call, if we don't get to your question in time, just reach out and we'll be happy to answer.
Feel free to email me, or I'll drop my email, and we can have a conversation.
All right, thanks.
All right, so we go to the next question. I believe that one is for Phil.
Yep. Phil, how to deal with the BRDF effect for the grazing angle GNSS-R? And I apologize, Ucia. I'm not sure what BRDF is. It looks like perhaps bidirectional reflectance distribution function. Is that correct? I don't know if
so I'm not quite sure how to deal with that, because I'm not quite sure what this person. We might need to have a bit more information. But if you're asking about the about how the reflectivity changes with the viewing geometry for grazing angle GNSS-R, I might have misread the question, but if that, or I might have hit it. So I apologize if I'm answering it incorrectly for what you're asking. But the reflectivity changes with the viewing geometry. At grazing angles, there's quite a bit more of a slope to these functions than there are near nadir, and so we see some of our observations, like the reflectivity and the phase noise, changing with the elevation angle, with quite a large dependence. But for our surface characterization, we, in terms of ice, sea ice characterization between the young ice, first year ice, and a multi-year ice, we're using a machine learning model, and that means that it's taking account of these viewing geometry aspects, because we feed it into that as well. Sorry, feed in the viewing geometry as well as the observables, and they're fairly simple functions, and it can be done through machine learning or through semi-empirical approaches.
Right. Thank you, Phil. Another question from CK on GNSS-R altimetry. Will there be a plan to construct code delay biased range altimetry? The purpose is to potentially have significantly more GNSS-R altimetry over areas which are incoherent. I believe.
So I'll take that. The level 1 data that we produce for on the grazing angle GNSS-R satellites does contain the code delay. It does contain everything that you need to be able to construct the code, the code phase or the carrier phase delay. One of the things that we are looking to do in the future is to combine the processing approaches so that we perform coherent observations on our near-nadir satellites as well as incoherent observations, and similar on the grazing angle satellites. So one of the ways in which we're improving our payloads is merging some of these processing characteristics between the two different types of reflectometry.
Thank you. If I could ask a quick follow-up question. I noticed that we could process level 1 data as we do like signals, DDM. I'm curious whether some kind of intermediate product like complex waveform may be available. And also all these very complicated corrections, antenna phase center, for cold range. So you don't have to worry about the phase altimetry because they will be canceled out. But all these other corrections for range will be very complicated depending on satellites.
So we provide in the level 1 data a number of the different fields that give information about how we would then go to our level 2 altimetry retrievals. We also go right back so that it's got a full sort of auditable trail from satellite attitude, the pod determination of the receiver position, and the raw observations without any ground processing. Through CSDA, we produce each of the different levels going up to the level 2. So that means that people aren't relying entirely on Spire to come up with the best level 2 algorithm. What we're hoping is that people will take the data and find ways of improving the approaches that are being used too. And we welcome people to work with us. We've got documentation for these products, and we welcome people working with us to help improve these too.
Thank you.
All right. In lieu of time, we are a few minutes over. So I would like to again thank everyone for taking the time out to join the Lunch and Learn. We will have the presentation and the recording available on the CSD website for access fairly soon after this webinar. So we definitely will let you know when it's out for you to browse through. Again, we again thank you for the time. Thanks, Spire, for putting this on. If you have additional questions that you could not get answered, please send them our way, CSDA way, and we'll make sure that we get them out to Spire for answers. Thank you, everyone, and have a great day.
Thank you.
Thank you, everyone, for attending.